At 11:47 a.m. on June 28, 1943, Corporal David Hughes stood outside the control tower at RAF Pembrey in South Wales, watching a single-engine fighter approach from the south. The morning was overcast. Visibility maybe 3 miles. The aircraft came in low over the Bristol Channel, wings level, gear down, standard approach. Nothing unusual except the sound. Wrong engine note. Not a Merlin, something deeper, harsher. Hughes raised his binoculars. The fighter was 400 yards out. He could see the radial engine, the wide cowling. Then he saw the markings, black crosses on the wings, swastika on the tail, German, a Focke-Wulf 190. Christ, Hughes said. German fighter inbound. The duty officer grabbed the phone. Scramble response. German aircraft landing. Repeat. German aircraft landing. But the Fw 190 wasn't attacking. It touched down smoothly at the threshold. Perfect 3-point landing. Rolled 300 yards. Turned toward the tower. The pilot was taxiing like he owned the place. RAF. Regiment soldiers sprinted from the guardhouse. 8 men with rifles. They surrounded the aircraft as it stopped 50 yards from the tower. The engine shut down. Propeller blades ticked to a stop. The canopy slid back. Oberleutnant Armin Faber stood up in the cockpit. He was wearing a standard Luftwaffe flight suit, life vest, leather helmet. He looked at the soldiers, looked at the tower, saw the RAF roundels painted on the building. His face went blank. No expression. Just recognition. He climbed down, raised his hands, didn't speak. Station Commander Wing Commander Gillen arrived 90 seconds later. He stared at the intact Fw 190, black crosses sharp against camouflage paint, no visible damage, engine still warm. Gillen walked to the phone in the tower, dialed fighter command directly. His hand was shaking. "We have an intact 190, he said. Repeat. Intact. The Focke-Wulf Fw 190 first appeared over France in September 1941. RAF pilots flying Spitfire Mark Vs encountered it during fighter sweeps near Saint-Omer. The combat reports were consistent and alarming. The new German fighter was faster in a dive, climbed better, rolled faster, and it could outrun a Spitfire at low altitude. Squadron leader Jamie Rankin flew Spitfires with 92 Squadron. On October 4, 1941, he encountered 4 Fw 192 near Abbeville. His combat report stated, "The enemy aircraft performed maneuvers. Our Spitfires could not match. When engaged, they simply rolled inverted and dove away. We could not follow." By December 1941, the statistics proved what pilots were reporting. RAF Fighter Command lost 154 Spitfires over France. German records showed 61 Fw 190 lost. The ratio was 2.5 to 1 inch Germany's favour. Worse than anything since the Battle of Britain. The performance gap was measurable. And Fw 190A could complete a full aileron roll in 3.2 seconds at 300 miles per hour. A Spitfire Mark V needed 4.8 seconds. In a turning fight, that difference was survival or death. The 10 Pu 190 climbed at 3,000 feet per minute. The Spitfire managed 2,400. In a dive, the Fw 190 reached 450 miles per hour before control stiffness became an issue. The Spitfire's limit was 380. American pilots reported the same problems. Captain Don Blakesley, flying P-47 Thunderbolts with the 4th Fighter Group, filed a report after an engagement near Lille in April 1943. The 190 can do things our fighters can't. It rolls faster, dives better. The German pilot controls the fight. We react. By spring 1943, Spitfire losses to Fw 190 had increased 40%, compared to 1,941 levels. Fighter Command tried new tactics, hit and run attacks, altitude advantage. Energy fighting. Nothing worked consistently. The W-190 was simply better in too many ways. Squadron leader Douglas Bader, a veteran with 22 kills, flew against FD-192nd in June 1941 before his capture. Years later, he said, "The 190 was the best fighter we faced until the jets. It could do everything well. We could do some things well. That's the difference." RAF intelligence collected combat film, studied gun camera footage, analyzed engagement patterns. The conclusion was always the same. The Fw-190 had advantages across the performance envelope: speed, climb, roll, dive. The only area where Spitfires maintained an edge was sustained turning radius at low speeds. One advantage against 6 disadvantages. Fighter command needed to understand why, needed to find the engineering secrets, needed to adapt Allied fighters to match or exceed German performance. But understanding required examination, real examination, not guesswork from combat observations. They needed an intact aircraft. Every pilot briefing included the same instruction. If you damage an FW-190, try to force it down intact. Do not destroy it if capture is possible. But capture was never possible. Damaged German fighters either made it home or crashed too hard for meaningful study. 9 months of trying. 9 months of failure. Until June 28, 1943. RAF Intelligence had examined 27 crashed Focke-Wulf 192nd by March 1943. Every examination revealed construction techniques, but nothing about why the aircraft performed so well. The first crash site was near Dover in November 1941. The aircraft had augered in at high speed. The engine was buried 8 feet deep. The wings had sheared off on impact. Recovery teams found pieces, brought them back to Farnborough for analysis. Engineers learned that the FW-190 used a BMW 801 radial engine, 14 cylinders, approximately 1,700 horsepower. They measured the wingspan, examined the control surfaces, documented the construction methods, but the aircraft was too damaged. They couldn't test it, couldn't fly it, couldn't measure actual performance. Crash analysis continued through 1942. 16 more Focke-Wulf 192nd went down over England or the Channel. All were recovered. All were too damaged. Burnt engines told engineers nothing about engine management systems. Shattered airframes revealed structural design, but not aerodynamic philosophy. Missing components left gaps in understanding. The engineers could see what the Germans had built. They couldn't understand why it worked so well. Wing loading calculations didn't explain the roll rate. Power-to-weight ratios didn't account for climb performance. Something about the integration of systems produced advantages greater than individual components suggested. Air Chief Marshal Trafford Leigh-Mallory reviewed the intelligence reports in January 1943. He read the crash analyses, read the pilot combat reports, read the loss statistics. Then he issued a directive to all RAF commands. Priority 1. Capture an intact W-190, not damaged, not partially destroyed. Intact. The directive went to Bomber Command, to Coastal Command, to SOE networks in France. Commandos planned raids on German airfields to steal an FW-190 off the ground. The plans were reviewed and cancelled. Too risky. Too many variables. Resistance networks received instructions. Locate forced. Landings. Secure the aircraft before German recovery teams arrived. Prevent demolition. Every fighter squadron received the briefing. Every mission included the same tactical guidance. If you damage an FW-190 badly enough to force it down but not enough to destroy it, escort it to a landing site. Prevent the pilot from crash landing deliberately. Every pilot understood. An intact 190 was worth more than 10 destroyed ones. But German pilots didn't cooperate. Damaged aircraft either made it home across the Channel or crashed catastrophically. The statistics were brutal. 27 examined. 0 intact specimens. The question everyone asked remained unanswered. What makes it so good? Then Armin Faber made his turn. The morning of June 28, 1943 started normally at Jagdgeschwader II's base at Beaumont-le-Roger in northern France. Oberleutnant Armin Faber was 23 years old. He'd joined the Luftwaffe in 1940, completed fighter training in 1941, posted to JG 2 inches March 1942. By June 1943, he had 8 confirmed kills. Experienced pilot, solid record, no disciplinary issues. The mission briefing was at 0945 hours. Intelligence reported RAF fighter sweeps expected along the French coast. Bombers possibly following. JG-2 would scramble to intercept. Standard defensive patrol. Faber's Staffel would fly 4 aircraft. He would be number 3 in the formation. They took off at 1015 hours. 4 Fw 190 A3 fighters. Faber's aircraft was Werk number 313. Factory fresh 3 months earlier. 72 flight hours on the engine. Everything functioning perfectly. They climbed to 18,000 feet, headed northwest toward the coast. Radio discipline maintained. Formation tight. At 1048 hours, they spotted the RAF fighters, Spitfires from 411 Squadron, Royal Canadian Air Force, 12 aircraft at 15,000 feet. The German flight leader called the bounce. They dove. Faber picked a Spitfire on the formation's left flank, closed to 400 yards. The Spitfire saw him, turned hard right. Faber followed. Got guns on target. Fired a 3-second burst. His wingman later confirmed hits on the Spitfire's fuselage. The British fighter rolled left and dove away, trailing smoke. Faber's 9th kill. But during the engagement, Faber's aircraft took hits. 2 20mm rounds from another Spitfire punched through his left wing. One struck the outer wing panel. The other hit closer to the fuselage. Both passed through without hitting critical structure. No fuel leak, no control damage. But the impact shook the aircraft hard. Faber felt the vibration through the stick. He broke off. Standard procedure after taking hits: check aircraft condition, rejoin formation if possible. His wingmen were still engaged. He was alone. He turned south. Heading home. That's what he thought. Combat disorientation is common after hard maneuvering. Faber had been pulling high G turns for 4 minutes, rolling, diving, climbing. His inner ear was confused, his sense of direction scrambled. The weather wasn't helping. Overcast conditions, no visible sun position, no clear horizon, just grey sky and grey water below. His compass was acting erratically. The vibration from the 20mm impacts had knocked something loose. The needle swung 15 degrees left and right, unreliable. Faber flew by instinct. South was behind him. South was home. He followed the coastline visible through breaks in the clouds, but he'd gotten turned around during the fight. He wasn't flying south along the French coast. He was flying north along the Welsh coast. The two coastlines looked similar from altitude: grey water, grey land, industrial areas visible inland. He saw an airfield ahead, assumed it was Brest or maybe Morlaix, one of JG-2's auxiliary fields. His fuel was low. The engine gauges showed 20 minutes remaining. Landing was the smart decision. He entered the pattern at 1,143 hours, lowered his landing gear, dropped flaps, lined up on the runway, everything normal. He touched down at 1,147 hours. Perfect. Landing. Rolled out. Turned toward what he thought was the operations building. Then he saw the soldiers running toward him. British uniforms. RAF roundels on the tower. The realization hit like a physical blow. This wasn't France. This was Wales. He'd landed at an enemy airfield. Faber shut down the engine, opened the canopy, climbed out with his hands visible. The soldiers surrounded him. Rifles pointed. He didn't resist, didn't speak. One soldier asked him something in English. Faber understood English, but didn't respond. Wing Commander Gillen arrived. looked at Faber, looked at the intact FW-190, asked the obvious question. "Which base did you think this was?" Faber answered in German. "Ich dachte, es wäre Brest." Gillan spoke some German. "This is RAF Pembrey, Wales." Faber said nothing. His face showed nothing. But he understood. He understood completely. He'd just given the British everything they needed to understand the FW-190, everything they'd been trying to capture for 18 months, and he'd delivered it with a perfect landing. At 12:03 p.m., 16 minutes after Faber's landing, Fighter Command received Wing Commander Gillan's call. The duty officer at Bentley Priory transferred the call directly to Air Vice Marshal Trafford Lee Mallory. Lee Mallory listened, said 3 words. "Secure that aircraft." Then he hung up and called the Air Ministry. By 12:45 p.m., intelligence officers at the Air Ministry had activated the FW-190 examination protocol. The protocol had existed since January 1943. Nobody thought they'd ever use it. Wing Commander Alec Ferguson at the Royal Aircraft Establishment, Farnborough, received orders to proceed immediately to RAF Pembrey. Take whatever personnel and equipment needed. Begin examination on site. Do not move the aircraft until initial assessment complete. Ferguson arrived at Pembrey at 2:15 p.m. by staff car. He brought 2 engineers from Farnborough, also a photographer and a technical illustrator. They went straight to the PERS, hangar where Faber's Fw-190 sat under armed guard. Ferguson walked around the aircraft slowly, twice, making mental notes. Then he began the official inspection. The aircraft was completely intact. No combat damage except 2 20mm holes in the left wing. Both holes were clean entry and exit wounds. No structural damage. The engine showed no signs of stress. Oil levels normal. Coolant normal. Fuel remaining in tanks, approximately 40 litres. Enough for another 15 minutes of flight. Ferguson opened inspection panels. Examined the internal structure. The first thing he noticed was the simplicity. Everything was designed for maintenance access. Panels secured with quick-release fasteners. Systems laid out logically. No wasted space. He dictated notes while the illustrator drew diagrams. BMW, 801 radial engine, 14 cylinders, 2 rows. Direct fuel injection visible. Oil cooling system separate from main cooling. Fan-assisted cooling. Unusual design. Ferguson moved to the cockpit, climbed onto the wing, looked inside. The cockpit layout was different from any British fighter. The throttle quadrant was on the left side. Single throttle lever. Ferguson knew British fighters required separate controls for throttle, mixture, propeller, pitch, and boost. This aircraft had one lever. He traced the control cables. Found a complex mechanical device connected to the throttle, multiple cam surfaces, linkages to the fuel system, ignition timing, propeller governor, and boost control. Automated engine management, Ferguson said. The pilot moves one lever. The system adjusts everything else. The engineers examined the control surfaces. The ailerons were large, positioned far outboard on the wing, but something was different about their balance. One engineer measured the hinge line position, then measured the control surface mass distribution. The ailerons had weights positioned forward of the hinge line. Mass balancing. It reduced control forces and allowed rapid roll, rates without excessive pilot strength. By 6 p.m., the initial examination was complete. Ferguson compiled his preliminary report. The list of technical advantages was longer than he expected. Automated engine management, mass-balanced controls, hydraulic actuation for flaps and landing gear, electric trim system, wide-track landing gear for ground stability, simplified maintenance access, superior pilot ergonomics. Each individual feature was impressive. Together, they represented a design philosophy fundamentally different from British practice. The Germans had optimized for pilot workload reduction. British designers optimized for maximum performance numbers. The Fw 190 was easier to fly in combat. That ease translated to tactical advantage. Ferguson called Leigh-Mallory at 6:30 p.m., reported findings, recommended immediate transport to Farnborough for complete examination and flight testing. Leigh-Mallory approved. But Ferguson had one more request. We need to work through the purser, night. I want this aircraft completely documented before we move it. The night shift began at 7 p.m. Additional engineers arrived from Farnborough, specialists in engines, armament, aerodynamics, and systems. They divided the aircraft into sections, each team responsible for one area. The photographer shot 340 photographs. Every panel, every system, every component. The illustrator created detailed technical drawings. The engine team removed cowling panels, examined the BMW 801 inches detail. The cooling system was sophisticated. The radial engine used a ducted cooling fan. Air entered through the cowling. The fan forced air through cooling fins. Hot air exhausted through controllable flaps at the rear of the cowling. The system maintained optimal engine temperature automatically. British radial engines used simpler cooling, but required constant pilot monitoring. The armament team examined the weapons installation. Two 7.92mm machine guns in the upper fuselage. Two 20mm cannons in the wing roots. The cannon installation was particularly clever. The weapons were mounted close to the fuselage centerline. Ammunition feeds were short and direct. British cannon installations in wings required long, curved ammunition feeds. Those feeds jammed frequently. The German installation was more reliable. The aerodynamics team measured everything: wing dimensions, airfoil sections, control surface areas. They calculated wing loading, compared it to Spitfire data. The W190 had higher wing loading but better performance. That contradiction suggested something about the airfoil design or the wing's structural efficiency. They needed flight testing to understand it. By 2 a.m., the examination teams had documented every accessible system. They'd removed inspection panels throughout the aircraft, photographed internal structure, measured cable tensions, checked hydraulic pressures, examined electrical systems. The aircraft was more sophisticated than any Allied fighter, not in dramatic ways, in hundreds of small details. Each detail reduced pilot workload or improved reliability or simplified maintenance. Ferguson compiled the night's findings. The report ran to 47 pages. Technical drawings, photographs, performance estimates, system descriptions. The conclusion was clear. The TEBU-190's advantages came from integration. Every system was designed to work with every other system. The result was an aircraft that was easy to fly, easy to maintain, and devastatingly effective in combat. At 6 a.m. on June 29th, Ferguson called Leigh-Mallory again. We're ready to transport, but we need a test pilot, someone with experience in German aircraft, someone who can evaluate this properly. Leigh-Mallory didn't hesitate. I'll call Eric Brown. Captain Eric Winkle Brown was the Royal Navy's chief test pilot for enemy aircraft evaluation. He was 24 years old. He'd flown 37 different aircraft types. He spoke fluent German. He'd studied aeronautical engineering in Germany before the war. If anyone could properly evaluate the FW-190, it was Brown. Brown received the call at 7:30 a.m. He was at the Royal Naval Air Station at Farnborough. The orders were simple. Report to the RAE. An intact FW-190 was inbound. Flight testing would begin as soon as the aircraft was cleared. Brown asked one question. How intact? Completely intact, Leigh-Mallory said. Perfect condition. Brown understood what that meant. For 18 months, RAF and Fleet Air Arm pilots had been dying to W-190 seconds. Now they had one. Undamaged, ready to fly, ready to reveal its secrets. This wasn't just a test flight, this was the intelligence breakthrough of the war. The third, 190, arrived at Farnborough at 11 a.m. on June 29th. transported by road on a special trailer. Guards accompanied it the entire way. It went straight into a secure hangar. More examination teams descended on it. But now the focus was different. Not documentation, preparation for flight, safety checks, system, functionality, fuel system inspection, engine run-up testing. Brown arrived at the hangar at 3 p.m. He walked around the aircraft, studied it, compared it mentally to every other fighter he'd flown. The Fw 190 looked purposeful, aggressive, the wide cowling, the tall landing gear, the bubble canopy. Everything about it suggested performance. He climbed into the cockpit, sat in the seat, adjusted it for his height. Brown was 5'7", small for a pilot. The cockpit fit him perfectly. He could reach every control without stretching. The visibility was excellent, better than a Spitfire. He studied the instrument panel, German labels, but the layout was logical: airspeed, altitude, engine gauges. Everything positioned where it should be. Ferguson briefed Brown on the systems, explained the automated engine management, the single throttle control, the electric trim, the hydraulic systems. Brown listened, asked technical questions, took notes. By 5 p.m., he knew the aircraft's systems as well as any pilot could without flying it. The first engine run happened at 6 p.m. on June 30th. Ground crews had checked everything: fuel system, oil system, ignition. Everything functioned. Brown sat in the cockpit. Ferguson stood beside the aircraft with a fire extinguisher. Brown followed the startup checklist they'd translated from captured German manuals. Fuel boost pump on, mixture control to rich, throttle cracked open, magnetos to both, starter engaged. The BMW 801 cranked, coughed, caught. 14 cylinders fired in sequence. The engine settled into a rough idle. Blue smoke from the exhaust. Normal for a radial on cold start. Brown advanced the throttle slowly. The engine smoothed out. The automatic systems took over. Engine speed stabilized. Oil pressure rose. Coolant temperature climbed. Everything working exactly as designed. Brown ran the engine for 20 minutes. Checked all systems. The automated engine management worked flawlessly. Moving the throttle, adjusted everything simultaneously. Mixture. Propeller pitch. Boost. The pilot just moved one lever. The complexity was hidden. That was the genius of it. At 7 p.m., Brown shut down, climbed out, looked at Ferguson. It's ready to fly. The first flight was scheduled for July 3rd, 1943. 3 days to complete final checks. 3 days for Brown to study the aircraft more. 3 days for the engineers to prepare instrumentation. They would measure everything during the flight. Speed, climb rate, roll rate, turn radius, dive characteristics, control forces, everything. The captured Fou 190 would reveal all its secrets. And those secrets would change how Allied fighters were designed for the rest of the war. July 3rd, 1943, 6:45 a.m. RAF Pembrey. Captain Eric Winkle Brown arrived at the secure hangar before sunrise. He was wearing standard Royal Navy flying gear, Mae West life vest, leather helmet, goggles. He'd flown 37 different aircraft types in his career. German, British, American, Italian. But this flight was different. This was the aircraft killing Allied pilots every day over Europe. Now he would fly it, understand it, find its weaknesses. The Fw 190 sat in the center of the hangar. Ground crew had fueled it the previous evening, conducted final inspections. Everything was ready. Brown walked around the aircraft one more time. His ritual. He touched the propeller blades, checked the landing gear oleos, examined the control surfaces, looked inside the engine cowling. Everything he saw impressed him. German engineering was meticulous. Ferguson approached with a clipboard. Final briefing before flight. They went through the systems again: startup procedure, takeoff speeds, emergency procedures. The Fw 190 had one dangerous characteristic. The BMW 801 engine had a tendency to cut out during negative G maneuvers. Carburetor icing. German pilots knew about it. Allied pilots didn't. That knowledge could save Brown's life. At 7 a.m., Brown climbed into the cockpit. The seat fit him perfectly. His feet reached the rudder pedals without stretching. His hands fell naturally on the control stick and throttle. The Germans had designed this cockpit for combat. Everything essential was within immediate reach. Everything else was positioned logically. No hunting for switches during a fight. Brown strapped in. 5-point harness. Tight. He connected his oxygen mask. Checked the supply. Good flow. He tested the radio. Static, then clear. Farnborough Tower. This is captured aircraft. Radio check. Captured aircraft. Farnborough Tower. Loud and clear. Brown ran through the pre-start checklist. Master electrical switch on. Fuel selector to main tanks. Fuel boost pump on. He could hear it whirring. The sound was different from British pumps. Higher pitched. He set the mixture control to rich. Cracked the throttle open 1 inch. The throttle moved smoothly, lighter than a Spitfire's throttle, less friction. He engaged the starter. The BMW 801 turned over, slowly at first, then faster. The engine caught on the 4th blade, 14 cylinders firing in sequence. The noise was enormous, deeper than a Merlin, more aggressive. Blue smoke poured from the exhaust stacks. The whole aircraft vibrated. Brown watched the gauges. Oil pressure rising, coolant temperature climbing. Everything normal. He advanced the throttle slowly. The automatic engine management system took over. The engine speed increased smoothly. No manual adjustment needed. No fiddling with mixture or propeller pitch. Just move the throttle. The systems did everything else. Brown smiled. This was brilliant engineering. At 7:12 a.m., Brown released the brakes. The Fw 190 rolled forward. The wide landing gear track made ground handling easy, more stable than a Spitfire, less tendency to ground loop. He taxied to the runway, tested the brakes, firm and responsive, tested the flight controls. Stick movement translated immediately to surface deflection. No sloppiness, no play in the system. Tower cleared him for takeoff. Brown aligned with the runway centerline, advanced the throttle to full power. The BMW 801 roared. The aircraft surged forward. Acceleration was immediate, brutal. The tail came up at 60 miles per hour. The TW 190 wanted to fly. At 105 miles per hour, Brown eased back on the stick. The aircraft lifted off after 400 yards, shorter takeoff roll than a Spitfire. The climb was impressive. Brown held 160 miles per hour. The rate of climb indicator showed 3,200 feet per minute, better than any Allied fighter except maybe the P-47. He climbed to 5,000 feet, leveled off. Reduced power to cruise setting. The automatic system adjusted everything. Smooth, effortless. Brown began the evaluation sequence. Straight and level flight first. He trimmed the aircraft. The electric trim system worked perfectly. Small thumb switch on the control stick. Press it. The aircraft trimmed. No wheel to spin. No taking your hand off the throttle. He flew, hands off, for 30 seconds. The W190 maintained altitude and heading without input. Stable, well balanced. Next test. Slow flight. Brown reduced power. Let the speed decay. 140 miles per hour. 120. 100. The controls remained responsive. No mushiness. At 95 miles per hour, the stall warning buffet began. Gentle. Progressive. Not the sharp brake of a Spitfire. Brown reduced power further. At 87 miles per hour, the left wing dropped. Clean stall. He applied opposite rudder. Released back pressure. The Fw 190 recovered immediately. No tendency to spin. Docile. The roll test came next. Brown accelerated to 250 miles per hour. applied full aileron deflection. The Fw 190 snapped into a roll, fast, violent. He completed a full 360-degree roll in 3.1 seconds. Faster than any Allied fighter, he reversed direction, full opposite aileron. The aircraft rolled the other way just as fast. The mass-balanced ailerons made all the difference. No heavy control forces, just quick, precise response. Brown climbed to 15,000 feet. Prepared for the dive test. This was critical. Allied pilots reported the W-190 could outdive anything. Brown needed to know why. He rolled inverted. Pulled through into a vertical dive, advanced throttle to full power. The airspeed increased rapidly. 300 miles per hour. 350. 400. The controls remained effective. No vibration. No flutter. At 450 miles per hour, Brown began to feel control stiffness. But the aircraft was still controllable. Stable. He pulled out at 8,000 feet. 4 Gs on the accelerometer. The Fw 190 handled it easily. No structural complaints. No trim change. The most important test. Combat maneuvers. Brown climbed back to 12,000 feet. Simulated an engagement sequence. Hard turn. Barrel roll. Split S. Chandelle. Immelmann. The Fw 190 performed every maneuver cleanly, precisely. The controls were beautifully harmonized. Stick forces were light but not too light. Just enough feedback to feel what the aircraft was doing. Then Brown discovered something unexpected. During a hard turn at 200 miles per hour, he deployed the combat flaps. The Germans called them Kampfklappen. The flaps extended 20 degrees. Suddenly, the turn radius tightened. Dramatically. The Fw 190 could turn with a Spitfire at this speed. The combat flaps changed everything. Brown made a note. This feature needed to be in Allied fighters. He tested the engine management system under combat conditions. Rapid throttle movements. Full power to idle to full power again. The automatic system handled everything. No hesitation. No stumble. No pilot workload. A British pilot would be adjusting mixture, propeller pitch, boost, and throttle. 4 controls. 4 separate actions. The German pilot just moved one lever. That difference meant more time for fighting, less time for systems management. At 8:03 a.m., Brown entered the landing pattern. Lowered the landing gear. The hydraulic system operated smoothly. Gear down and locked in seconds. He deployed full flaps. The W-190 slowed rapidly, very draggy with flaps extended. Good for landing. He crossed the threshold at 100 miles per hour. Reduced power. Flared. The wide landing gear made touchdown easy. No ground loop tendency. No bouncing. The Fw 190 rolled out straight and true. Brown taxied back to the hangar. Shut down the engine. Sat in the cockpit for a moment, processing what he'd just experienced. This aircraft was exceptional. Not perfect, but exceptional. The automated systems, the control harmony, the performance, everything worked together. That was the secret. Not one brilliant feature. Everything supporting everything else. Ferguson met him at the aircraft. Well? Brown climbed out, pulled off his helmet. It's not one thing making it so good. It's everything. The whole aircraft is designed to reduce pilot workload and maximize combat effectiveness. We've been designing fighters wrong. Ferguson wrote that down. Explain. Brown thought about how to phrase it. We design for maximum performance numbers. Top speed. Climb rate. Turn radius. The Germans designed for the pilot. They asked, what does the pilot need in combat? Then they built systems to provide it. Less workload means more situational awareness. More awareness means better tactics. Better tactics mean more kills. Can we adapt these features? Brown nodded. The combat flaps. The mass-balanced ailerons. The automated engine management. All of it can be adapted. Some of it can be retrofitted to existing fighters, some will require redesign. But yes, we can do this. Ferguson smiled for the first time in 3 days. Then we will. Brown filed his report that afternoon. 23 pages. Technical analysis. Performance measurements. Tactical implications. Design recommendations. The report went to the Air Ministry, to Fighter Command, to the Ministry of Aircraft Production. Within 48 hours, it was on every senior officer's desk. Within a week, American observers requested copies. Within 2 weeks, engineering teams from Supermarine, Hawker, North American Aviation, and Republic Aviation were reading Brown's findings. The captured FW-190 had revealed its secrets. Now the question was, how fast could Allied engineers adapt those secrets into combat advantages? On July 8, 1943, at Wright Field in Dayton, Ohio, Colonel Benjamin Kelsey sat in his office reading a classified telegram from London. Kelsey was Chief of Fighter Projects for the United States Army Air Forces. Every American fighter development program crossed his desk. Every performance report. Every combat evaluation. He'd spent 2 years trying to solve the Fw-190 problem. American pilots reported the same issues as the British. The German fighter was better, faster in a dive, better roll rate, superior climb. Now the telegram from London offered a solution. British have captured intact Fw-190. Stop. Complete evaluation underway. Stop. Request American technical team for joint examination. Stop. Aircraft available for testing. Stop. Kelsey read it twice. Then he called his deputy. Get me a team. Engineers. Test pilot. I want them in England in 48 hours. The team assembled quickly. Major Thomas Hitchcock, a P-51 specialist who'd flown combat missions with the 8th Air Force. Captain Fred Borsodi, test pilot from Wright Field, with 200 hours in German aircraft. 3 engineers from Republic Aviation, manufacturers of the P-47 Thunderbolt. 2 engineers from North American Aviation, makers of the P-51 Mustang, 8 men total. They left Wright Field on July 10th, arrived at RAF Farnborough on July 14th. Wing Commander Ferguson met them at the hangar. The FW-190 sat under floodlights. The Americans walked around it slowly, not speaking, just looking. Hitchcock stopped at the nose, studied the BMW 801 engine. The cowling design was different from any American radial installation, cleaner, more integrated. Borsodi examined the cockpit, climbed up on the wing, looked inside. He stayed there for 5 minutes. Taking it in, Ferguson briefed them on the examination findings, the automated engine management, the mass-balanced ailerons, the combat flaps, the wide landing gear, the hydraulic systems. He showed them Brown's test report, performance measurements, control force data, roll rate graphs. The Americans took notes, asked technical questions. Ferguson answered everything. The British had one condition for full cooperation: complete sharing of findings. Any adaptations developed by American manufacturers would be shared with British designers. The Americans agreed. The examination began that afternoon. The American team divided into specialties. The Republic engineers focused on the engine installation. Their P-47 used a Pratt & Whitney R2800 radial, similar configuration to the BMW 801. They needed to understand the German cooling system, why it worked better. The cowling design used ducted cooling with a controllable exit flap. Air entered through the cowling nose, flowed, past the cylinders, exited through flaps at the rear. The flaps opened or closed automatically based on temperature. Simple, effective. The P-47 used a different system, less efficient, more prone to overheating. This German design could solve that problem. The North American engineers studied the airframe, specifically the wing and control surfaces. The P-51 had excellent performance, but poor roll rate at high speeds. The aileron control forces became too heavy. Pilots couldn't roll quickly in combat. The Focke-Wulf 's mass-balanced ailerons solved this exact problem. Weights positioned forward of the hinge line. The weights counteracted aerodynamic forces at high speed. Roll forces remained light. The concept was simple. Implementation would require testing, but it could work. Borsodi flew the Fw-190 on July 16th. Ferguson accompanied him through pre-flight. Explained the systems again. Borsodi had flown captured Bf-109 seconds before, but the W-190 was different, more refined, more sophisticated. His test flight lasted 7 minutes. When he landed, he went straight to Hitchcock. Everything they said is true. This aircraft is easier to fly in combat than anything we have. The automation, the control harmony. All of it. Hitchcock asked the critical question. Can we adapt it to our fighters? Some of it immediately. Some will take time. But yes. The American team spent 3 weeks at Farnborough. They measured everything, photographed everything, documented every system they could access. They flew the W-196 more times. Different pilots, different test profiles. Each flight revealed more details. The combat flaps reduced turn radius by 18% at 200 miles per hour. The mass-balanced ailerons allowed roll rates 30% faster than a P-47. The automated engine management reduced pilot workload by an estimated 40% during combat. On August 3rd, Kelsey sent a request to the British Air Ministry. The Americans wanted a second W-190 shipped to Wright Field. For detailed examination by American manufacturers, the British agreed on one condition. They needed another intact specimen first. They wouldn't give away their only example. Luck provided the answer. On August 4th, another W-190 made a forced landing in England, this one near Manston in Kent. Engine failure. The pilot, Unteroffizier Hans Norman, landed in a field. British troops captured him before he could set demolition charges. The aircraft had minor damage. Repairable. The RAF recovered it. Sent it to Farnborough. Now the British had 2 Fw-192s. They could spare one for America. The second aircraft was prepared for shipment. Non-essential equipment removed to reduce weight. The aircraft was partially disassembled. Wings removed. Tail section detached. Everything packed in custom crates. On August 5th, the crates were loaded onto a transport ship at Liverpool. Destination, New York. The voyage took 23 days. The ship arrived on August 28th. The crates were transferred immediately to a military train. Shipped to Wright Field. Arrived August 30th. Reassembly took 4 days. American engineers worked around the clock. By September 3rd, the Fw-190 was complete, ready for testing. But Kelsey had different plans. Before flight testing began, he wanted the aircraft completely disassembled. Every component examined, every system documented, every design principle understood. This was intelligence. This was engineering school. The Americans would learn everything the Germans knew about fighter design. The disassembly began on September 7th. Teams from Republic, North American, Lockheed, Curtiss, and Bell Aircraft descended on Wright Field. 50 engineers, all working on the same aircraft. They divided it into sections: engine, airframe, systems, controls, armament. Each team had one assignment: understand their section completely, document everything, determine what could be adapted to American fighters. The engine team removed the BMW 801, mounted it on a test stand, ran it for 40 hours under various conditions. They measured fuel consumption, power output, cooling efficiency. They disassembled the Commando Jarrett, the automated engine control device. It was mechanically complex, dozens of cam surfaces and linkages, but the principle was simple: one input from the throttle, multiple outputs to engine systems. The team photographed every component, drew detailed schematics, calculated cam profiles. Within 2 weeks, they understood how it worked. More importantly, they understood how to build an American version. The airframe team focused on the wings and control surfaces. They removed both ailerons, weighed them, measured the mass balance weights, calculated the center of gravity relative to the hinge line. The math was straightforward. The weights moved the control surface's center of gravity forward of the hinge. At high speeds, aerodynamic forces tried to trail the aileron. The mass balance counteracted those forces. Result: light control forces at all speeds. The team calculated that similar weights could be added to P-47 ailerons. No major redesign needed, just add weights. Test, adjust, deploy. The systems team examined the hydraulic and electrical systems. The Fw-190 used hydraulics for landing gear, flaps, and some control surface boost. The system operated at 150 bars pressure. Higher than American standards. Higher pressure meant smaller actuators, lighter weight, but also more potential for leaks. The Germans used different seals, different materials. The American team documented everything. Some of it could be adopted, some couldn't. Different manufacturing standards, different available materials. By late September, the examination was complete. The teams compiled their findings into reports. Republic Aviation's report was 187 pages. North American's was 214 pages. Each report contained the same conclusion. The W190's advantages came from integrated systems design. Every component was designed to work with every other component. The result was greater than the sum of parts. More importantly, the reports contained recommendations, specific modifications to American fighters, changes that could be implemented immediately, changes that required more development, changes that would make American fighters competitive with the FW-190. The question now was simple. How fast could American industry adapt these lessons? How quickly could the modifications reach combat units? The answer would determine how many pilots lived or died in the skies over Europe. Wright Field, September 1943. 3 teams worked in separate hangars. Each team had one disassembled section of the W-190. Each team had one mission: extract every design principle. Understand every advantage. Find what could be adapted to American production fighters. The airframe team started with the wings. Chief Engineer Robert Marsh from Republic Aviation led the examination. He'd designed portions of the P-47's wing structure. Now he was looking at German engineering. The Fw 190 wing used a single main spar with a torsion box forward of it. American fighters typically used multiple spars. The German approach was simpler, lighter. But was it stronger? Marsh's team conducted structural tests. They mounted wing sections in a test rig, applied loads, measured deflection. The single-spar design was actually stronger per pound than multi-spar construction. The torsion box handled twisting loads better than traditional rib construction. This wasn't just different engineering. This was better engineering. The aileron examination revealed the mass balance secret in precise detail. Marsh removed the left aileron, placed it on a balance table, measured the center of gravity. Without the balance weights, the center of gravity was 2.3 inches behind the hinge line. With the weights installed, it was 0.4 inches forward of the hinge line. That shift was everything. At low speeds, the position didn't matter much. At high speeds, aerodynamic forces increased dramatically. An aft center of gravity meant those forces would push the aileron trailing edge up. The pilot would have to fight those forces. Heavy stick, slow roll rate. A forward center of gravity meant the mass of the aileron itself counteracted aerodynamic forces. Light stick, fast roll rate. Marsh calculated the exact weight and position needed for a P-47 aileron. The P-47's aileron was larger than the FW-190's. Different shape, different hinge line. But the principle was identical. Add 3.2 pounds of lead weight. Position it 4.1 inches forward of the hinge line. The math predicted a 35% improvement in roll rate at combat speeds. The team fabricated the weights, installed them on a P-47D at Wright Field. Test pilot Major Harold Johnson flew it on September 22nd. His report was enthusiastic. Roll rate is dramatically improved. At 350 miles per hour, I can now complete a full roll in 2.8 seconds versus 4.1 seconds stock. Control forces are lighter. Response is immediate. This modification should be implemented fleet-wide immediately. The wing team also examined the landing gear geometry. The Fw 190's main gear was positioned far outboard on the wing. Track width was 2.84 meters. Compare that to a Spitfire's 1.73 meters or a P-51's 2.29 meters. The wide track had massive implications for ground handling. Narrower gear meant higher probability of ground loops, especially with high-power radial engines. The P-47 had particular problems. 23% of P-47 accidents were ground loops during landing or takeoff, but the American team couldn't change existing landing gear. Widening the track would require complete wing redesign. This finding would influence future designs, not current modifications. They documented it for the next generation of fighters. The engine team worked in a separate building. The BMW 801 sat on a test stand, instrumented with dozens of sensors, temperature probes, pressure, transducers, fuel flow meters, dynamometer for power measurement. Chief Engineer William Huber from Pratt & Whitney ran the tests. His company built the R2800 engine that powered the P-47. He needed to understand why the German engine's cooling was so much better. The key was the cooling fan and ducting. The BMW 801 used a 14-blade cooling fan directly behind the propeller. The fan pulled air through the cowling, forced it past the cylinder fins. The air then exited through controllable flaps at the rear of the cowling. The flaps opened or closed based on cylinder head temperature, automatic temperature control. No pilot input required. American radial engines used a different approach. Cowl flaps that the pilot opened or closed manually. The system worked, but required constant monitoring. Open the flaps too much, and you lost speed. Close them too much and the engine overheated. German pilots didn't manage cooling. The system managed itself. Huber's team measured the cooling efficiency. The BMW 801 maintained optimal cylinder head temperature across a wide range of power settings and airspeeds. The automatic flaps adjusted continuously. The American system showed greater temperature variation, less efficient, more pilot workload. Could the automatic system be adapted to American engines? Huber thought, yes, but it would require redesigning the cowling, adding temperature sensors, adding an actuator for the flaps, adding a control unit. Possible, but not quick. Not something that could be retrofitted to 4,000 P-47 seconds already in service. This was for future production. New aircraft, not current modifications. The most revolutionary system was the Kommando Gerät, the automatic engine control device. Engineer Franz Schneider from Wright Field led this examination. Schneider was German-American. His father had been an engineer with Mercedes before emigrating in 1928. Schneider spoke fluent German. Read German technical documents easily. He studied the Kommando Gerät like it was a mechanical puzzle. The device was mounted on the engine. It received input from a single throttle cable. It produced 9 outputs: fuel flow to the injection system, propeller pitch control, ignition timing advance, boost pressure control, mixture ratio, oil pressure, cooling flap position, supercharger gear selection. Everything except the magneto switches. Schneider disassembled it completely. The core was a stack of cam plates. Each cam had a 3-dimensional profile. The throttle input rotated the cam stack. 9 followers rode on the cam surfaces. Each follower connected to a control rod. The cam profiles were precisely calculated to provide optimal settings at every throttle position. The mechanical computer solved 9 equations simultaneously. Instantly. Perfectly. Every time. American engines required the pilot to solve those 9 equations manually. Adjust throttle, adjust mixture, adjust propeller pitch, adjust boost, monitor temperatures, adjust cowl flaps. The workload was enormous, especially during combat when you needed to change power settings constantly. Schneider calculated that building an American version of the Commander Jarrett would take 18 months. Design the cams, build prototypes, test, refine, produce, install. Too long. But he had another idea, a simpler version. Maybe just control 3 functions automatically: mixture, propeller pitch, and boost. Leave the rest manual. That could be done in 6 months. Good enough. Not perfect like the German system, but better than full manual control. The systems team examined every other component. The electric trim system. Simple. Just an electric motor connected to the trim tabs. Push a button, the motor ran, the tabs moved. American fighters used manual trim wheels. The pilot had to spin the wheel, sometimes dozens of turns. During combat, that meant taking your hand off the throttle. German pilots kept both hands on the controls. Huge advantage. Could electric trim be retrofitted? Yes. Relatively simple. Add a motor. Add a switch. Add wiring. The modification could be done at depot level, maybe even in the field. This went on the immediate implementation list. The hydraulic system examination revealed German preferences for higher operating pressures. 150 bar versus American standard of 105 bars. Higher pressure meant smaller actuators, lighter components. But American seals and hoses weren't rated for 150 bars. Using higher pressure would require new components, new suppliers, new qualification testing. Not worth it for existing designs, but future aircraft would benefit. By October 15th, all 3 teams had completed their examinations. They compiled a master report. The findings were organized by implementation timeline. Immediate modifications. Mass-balanced ailerons for P-47. Combat flaps for P-51. Electric trim for both. Timeline: 60 to 90 days. Near-term modifications. Simplified automatic engine control. Improved cowling. Design. Timeline: 6 to 9 months. Long-term changes. Complete redesign incorporating all principles. Timeline: 18 to 24 months for new aircraft types. The report went to General Henry Arnold, Commanding General of the Army Air Forces. Arnold read it in one sitting. Then he called a meeting. Every fighter manufacturer representative. Every senior Air Force procurement officer. The meeting happened on October 22nd at the Pentagon. Arnold spoke for 10 minutes. His message was simple. We have been building fighters wrong. The Germans understood something we didn't. Pilot workload matters. System integration matters. We will adapt every lesson from the captured Fw 190. We will do it fast. I want modified aircraft in combat by January. I want new designs incorporating all principles by mid-1944. Questions? Nobody had questions. Everyone had assignments. Republic Aviation would modify P-47 ailerons. North American would redesign P-51, combat flaps. Both companies would implement electric trim. Pratt & Whitney would develop simplified automatic engine controls. Wright Field would coordinate flight testing. The 8th Air Force would prepare squadrons to receive modified aircraft. The timeline was aggressive. 90 days from decision to combat deployment. But the statistics justified the urgency. American fighters were losing to W-190 seconds at unacceptable rates. Every week of delay cost lives. Every modification that reached combat squadrons saved pilots. One captured aircraft had revealed the secrets. Now, American industry would prove it could adapt those secrets faster than Germany could develop new advantages. September through December 1943. 4 parallel programs. 4 American companies racing to adapt German engineering lessons into combat modifications. The timeline was brutal. 90 days from design to deployment. In peacetime, aircraft modifications took 18 months. Testing, certification, production. But this wasn't peacetime. Republic Aviation, Farmingdale, New York, September 28, 1943. Chief Engineer Alexander Kartveli received the mass balance specifications from Wright Field. He gathered his aileron design team, 7 engineers. One assignment: design mass balance weights for P-47D ailerons. Make them work. Make them reliable. Make them manufacturable. Timeline: 30 days.